Jon joined Breault Research in 2003. He has worked in technical support as well in training engineering services. His specialties include wave optics, polarization, color science, constructive geometry. He's done training sessions all over the world. He's very familiar doing webinars. He graduate work in optical science at the University of Arizona in nonlinear optical materials. He was previously at Allergen Technologies Lightwave Division and several parts of IBM.
We'll put that aside and talk a little bit about some of the things that I like about the latest ASAP NextGen. I've been using ASAP NextGen. I've taught a bunch of classes in the last year using ASAP NextGen. Recently, I've been playing with some of the features that are actually coming in beyond the initial offering. So forgive me for the sort of dual screen here. I have two things going on. I have ASAP going on, and I have a PowerPoint presentation inset because I kind of need to move back and forth very freely between the two. And I hope you'll be able to see everything okay. I'm actually looking at three screens now, and I'll just try not to confuse myself too much. Let's just plunge into this a little bit. I'm going to try to give you a little bit of information that some of you may have already seen in a previous presentation that is kind of an overview of what makes NextGen NextGen. And then I'm going to try to go into pretty pictures that are, well, altogether more fun for me. ASAP NextGen is, among other things, essentially a complete rewrite of the ASAP graphical user interface. There are other things we can say about NextGen, but I am going to focus on the things that you can readily see in the user interface. And I'm really going to focus mostly on ways of viewing interesting measurement data about a system. Just to be fair to those other things, which people put quite a bit of work into, we modernized the architecture under the covers. In other words, things like the way the user interfaces talk to the computational parts, as well as parallelization in the kernel that makes us able to speed up many kinds of calculations and ray traces significantly. And we had done it using remote before. We allow you to do it automatically now. So those are just a few of the factors in what makes NextGen NextGen. Let me talk just a little bit about the interface, and I'm not going to dwell on it too much. And then we're going to talk a little bit about various managers, and then we're going to talk about viewers, which is where I'm going to spend most of my time. And I'm going to talk about the viewers that let us see very colorful things. And when I say color, I'm not taking it lightly. So you will see what I mean. So briefly on the interface, a main window and a bunch of managers that allow us to deal with different aspects of our workflow and different forms of workflow, from very graphical to very script-oriented, and with a hybrid in between. Also managers for catalogs of properties, sources, lenses, and so on. And there are managers for looking at the macros you have in your current script, for example, user input screens, templates, and other kinds of tools. And the viewers, which, as I said, I'm going to concentrate on to let us view the results of what we do. So just briefly, we have in the user interface three key managers that we like to talk about. And two of the three are, in fact, new with the current graphical user interface. The optics manager, which is very graphically oriented and very tree oriented. The workflow manager, which helps us to look topically at specific operations and find the commands that apply. And third, scripting, which is the way deep under the covers we always talk to the computational part, but we can spare you having to speak that language fluently by the use of the first two. And so the script manager is our way of managing that actual scripted interface or interpreter to the kernel. One key thing is that the first two automatically write script commands that can be saved, archived, and run using the script manager. So let's just talk about the optics manager briefly. Sorry about the flicker. I have a hair trigger. We basically have always talked in the past about a four-step process. And whether you've had one of our classes or not, the key thing to know is that we divide the modeling process into 4 steps. And we capture them in a tree structure. And essentially, if you take a look at the points here, we have geometry, sources, trace, and trace analysis. The others are accessory, but we consider them to be, in a sense, accessories to the other steps. So I won't dwell on that too much. And just to be fair, I want to share with you what I'm talking about with a magnifier so that you really get it. So we have geometry, sources, trace, and trace analysis. The source analysis is just to make sure that we created the sources we intended to, the right energy, the right patterns, whatever it is. And the system settings and variables are kind of like providing the right header, setting the state for the rest of the model. And just to prove to you that I'm not making all this up, let me flick the Optics Manager in ASAP and actually show you the Optics Manager, which is live in ASAP now. And indeed, those are the steps we have. And later, I'll open something in the Optics Manager just to show you what it looks like when it's populated with something. And we'll actually play with it a little bit. Okay, so now I'm going to get rid of my magnifier for a moment and go back to the PowerPoint presentation. So, okay, we have the Optics Manager. And we can easily add optical system information like the physical geometry and the sources. You look things up by topic, but then you actually find out what command is related. You don't have to know the command because it gives you guidance. It actually shows you individual parts of the syntax. Now, let me just zoom in a little bit here just to show you briefly. It's a little fuzzy, but for the command, it shows you what the arguments are. It shows you which ones are required, and it puts the help there right next to it so that if you want to understand the command a little bit or you don't understand what it's asking for, the help will give you deeper remarks and explanations of what they are than you can fit into the header of the command line that we're entering into or the little form that we're filling out. It's basically like a 2-line form, 1 line that you fill in, 1 line with headers. So it's a very good tool for learning the language or for using the language without knowing all the details. Basically, we work our way through workflow by going down the tree and then out the branches. And that workflow then implements the actual syntax of commands. And those can be dropped into a script for use. And the key is the help helps you, matches the syntax, and explains it more. And the color coding helps you to know what you must do and what you may avoid or what you may ignore. Just briefly, I'm going to talk a little bit about script and macro managers. The key thing is the script manager itself is, for those who are familiar with ASAP, the same old script manager that we always had. In some respects, it has some features here that are new. You may see, if you use an older version of ASAP, you see some icons here in the editor pane that you may not be familiar with, but those do some additional things that we haven't done in the past. And I'll talk about one of those in a minute. We have all of the file types show in the File tab, and any of those files can be opened by right-clicking on the type in the tree, or we can use the Open and New to open new file types. But this lets us manage opening files and seeing what is actually present, and also just browsing the files that are available to us in the working directory. We have settings, preferences for the editor and other tools, managers, and so on as well. So that is the preferences up here. So let me just talk about one of the managers that is really cool and useful, and that we haven't talked a lot about in the past, the macro manager. It actually lets us see the macros that are available in the script that we're working on. So if you have a script with a lot of macro definition, it lets us see what we've done without having to go through the script to find it. So that is a useful thing. So let's just imagine for a particular script that we're working with, we turn on the macro manager and we actually see a list of macros. In this case, it's just a couple of them, but we see a list of macros, and if we select one here, it actually shows the macro code here. I write things that have mazes of macros, and this makes it much easier to see what I have. And maybe in a future webinar, I would spend all my time showing how we manage macros in libraries. So with that, I'm going to start getting at how we get output, how we get pretty pictures, how we get impactful and meaningful pictures that relate to a specific measured quantity in ASAP. Things that viewers do. They let us look at the system geometry, ray traces, distribution data of many, many kinds. We'll talk about a couple of them today. We can look at the Poincare sphere polarization map, conformal radiometry results, CIE colorimetry results, and we have added recently visual appearance. Visual appearance was a feature that came into Apex, and people who had both ASAP and Apex then began asking, how quickly can we have that in ASAP? Now we do. And we don't just have it, we have it in many forms, and that's what most of the rest of my talk is going to be about. The key thing with this is that we now use a computational kernel-based CIE colorimetry. It used to be actually part of the graphical user interface, but when we refactored, we put it into the kernel, and it's much faster and more efficient. We maintain some really interesting data structures that are useful, and I'm going to give you just a taste of what that's like. So we have tri-stimulus values, photometry results, that's in a sense redundant, chromaticity coordinates, correlated color temperature are available in the CIE viewer. And that is as before, but in a sense better because the data structures are now open to you so that you can do what you want with those data. It's not captive to just the CIE viewer, but that's one very good way to look at it. We can examine visual appearance of the converted tri-stimulus values, the XYZ tri-stimulus values, to an RGB or sRGB space in visual appearance viewer. And the visual appearance viewer is actually supplemented by being able to look at visual appearance and other of these quantities. Basically all of these that I'm showing here can be viewed also in the 3D viewer, and I will show you a dramatic example of that in a couple of minutes. So this is just an example of system geometry being shown in the 3D viewer. This is a 4-pane filter, basically clear, red, green, and blue, and well, red, green, and blue, or maybe it's orange, green, and blue. I actually have both versions of that filter. The CIE viewer, which many of you may recognize from previous versions of ASAP, but it isn't actually the same viewer. It merely mimics a layout that a lot of you said you liked. It has a chromaticity diagram, which can be in any one of the 3 color appearance models, going back to 1931, 64, 76, I guess. A display viewer that shows one of the color quantities at a time in physical space map, and then the actual data for every point. Basically, for every pixel in the display map, there is a point in the chromaticity diagram, and that point is also shown in an actual tabular data form. And I'll show you a little more about that later in live ASAP. And visual appearance is, in effect, very similar to this view, but specifically showing us what the human eye renders when looking at the thing we're measuring, the measurement window. And so for the 4-pane filter, we might see a result like this, where each of the parts, and this is one of the 3 tristimulus values, each of the parts is viewing, in a sense, a distinct component of tristimulus. This gets them all, and then the other 3, in a sense, are weighted, are showing us which tristimulus value is dominant by which one has more energy coming through, if you're familiar with tristimulus XYZ. Now with visual appearance, we can actually see what's coming through in color. So if we illuminate with a white source, and white might be any one of the CIE illuminants, the D illuminants, the E illuminant, for example. And I'll show you what I mean by that a little more in a few minutes. But if we illuminate with white, then the blue filter is going to look blue in transmission. The green filter is going to look green or yellow-green, depending on exactly where its center is. And the red filter may look red or orange, depending on where its center, pass band center is. So now that I've given you kind of I won't say the dry stuff, but the background on what is there, let's talk about 2 kinds of problems and look briefly at the results. The first is a camera system. We're actually going to create a source for the camera by taking an object and illuminating it. And we're going to then, from that illumination object, send the rays selectively just to the entrance pupil of the lens, which is very efficient. It lets us get extremely effective throughput between this picture that we're using as a source and the focal plane of the camera system. And we're going to look at the visual appearance in the image plane, and I will say image appearance at or not the image plane. It doesn't have to be at the image plane. It can be wherever we like, and I'll show you what that means in a minute. I'm also going to show you briefly a linear variable transmission filter. It's a visible wavelength transmission filter where the pass band center varies as we move along the Y direction in the filter. So it actually runs from a pass band that is deep in the blue to a pass band that is deep in the red, smoothly and linearly in wavelength space as we move along Y. We examine the transmitted light. We use 2 different definitions of white to illuminate it and see what that does. And we're actually going to see a qualitative obvious difference in what the human eye would see. We can also look at quantitative, but sometimes qualitative is nice for quick work. And one of the things that I'll also show you briefly is how to use the optics manager to run some of this analysis so that you can understand how to do it without necessarily having to know how to write the script for the color analysis itself. Those of you who have been with ASAP for a long time may remember, I haven't even been with ASAP this long, but I still remember the Parrot paper from the Optical Design Conference 1998, where a bitmap image was of 2 parrots at the time. I'm doing 1 parrot now. Was imaged through a system. So we turned the bitmap into a source, radiating with that color profile. We ran it through a lens system, and we looked at the result at the focal plane. Also did some ghost analysis in the paper. If we create this source, trace the rays, look at the focal plane, we will see, and I'll show you this in a few minutes live, we will see some planes that look kind of like the parrot, but not exactly. They look like they are color skewed. The reason for that is that this is a false color image. By default, the false color image is a false color image that happens to be tristimulus X because it's the first thing in the list. If we click on it, right click on it, then we get a choice to select the chromaticity data type, and we can actually look at a thing called visual appearance. And if we do that, that false color image turns into a real color image that shows us the image of the parrot. And yes, it's upside down because this is an imaging system, and imaging systems usually invert the image unless they're something more complicated than the typical camera lens, or just created for a different reason. So that's the basic idea. And I'll run through the slides first, and then I'll show you live in ASAP what this really means. So it's a compact camera. You know that by the fact that the focal length is extremely short. It's an f2.8 lens, and it has about a 25-degree semi-field of view. And we're using a bitmap image as an RGB source. There's a dummy diffuser in front that diffuses towards the entrance pupil selectively, and we get an image. This just shows you a cutaway of the lens system. I think the largest aperture in this system is on the order of, it's between 5 and 6 millimeters. So you get an idea of how small this lens system is. The object bitmap is effectively imaged using importance sampling, which is a great tool for stray light and other kinds of analysis, but in this case, for something completely different. And the color science tools that we use collect the tri-stimulus, chromaticity, color temperature, and visual appearance data for display. And just to show you kind of the upshot, if we go to that focal plane in the example I'm going to show you, we will actually see two images stacked one on top of another. One at the nominal focus, the nominal image plane, another that is 200 microns back, so it is defocused somewhat. And I think even with whatever difficulties we may have in imaging here or in our network communication to you, I believe you can clearly see that this is a fuzzy parrot, and this is a clearer fuzzy parrot. And just to compare those side by side, somewhat bigger so that it's a little bit more obvious, you see the nominal focus image and the 200 micron defocus image. So that is the first example, and I'm gonna go to ASAP, and we're going to take a real look at this before we go further. So I'm going to orient a particular way, and then I'm going to make a few things clear, get things out of our way. It won't be obvious to you yet, but I'm going to do what I said I was going to do, select the chromaticity type, change to visual appearance. You still don't see anything happening yet. Don't worry about that. Because I'm going to zoom in for maximum impact after I have everything set up for you. So I'm going to make some key components at the back end of the camera transparent. Just so you know how I'm doing that, I'm right-clicking on them and not hiding, but making transparent. So I can also do that just by hitting this and hitting the letter T. You can see that by looking at the code here next to transparent in the menu. So I've now made a couple things at the back end transparent. Now I'm going to actually zoom in, and I can do that. I can zoom in right behind the image by doing a zoom extents on this. And there it is. And as you can construct in your mind, as you can see, the out of focus image, the 200 micron defocus image, is behind the nominal focus image because I'm plus 200 millimeters defocused. So it's plus in plus Z, it's behind it. So now I am going to make sure that I have done some other things to make this clearer to you. I'll show you the focused and defocused images more clearly in just a minute. But for now, what I want to show you is that, let's see, I did not make the diffuser transparent yet, so let's do that. So now, let's ease back, zoom out, and see what happens. And you say, what is this color tiled wall behind us? Well, the color tiled wall behind us is the parrot, the original, the source. And so what I am showing you is that the parrot that the camera is imaging is in the distance, and the focal plane is back here at the end of the lens. And so just to the rectangle around the image right now is basically the image surface. And I've made it transparent so that it's clear, I hope, what you're looking at. And you can see that this is a live view because I'm actually rotating it. I don't have all the, focus mechanism and stuff like that in the lens. It basically is just the lens elements and a barrel without any of the mounting structures, but it shows you the basic layout of the lens. And so that is the first system that I wanted to demonstrate for you. And just to prove to you that I really can focus, I'm going to just delete this parrot image that is 200 microns out of focus. And that caused me to zoom out. Okay, I come back in, and now this is the focused image. So, so that is the first example I wanted to show you. And now I'm going to go back and find some of my other favorite examples to show you very quickly. So the second problem I want to talk about, and I'm going to go back to PowerPoint just long enough to show you what I'm talking about. I've got a bandpass filter. This is the green thing here in the middle. I'm illuminating it with something, with a source that I call white. Talk more about that in a minute. And then I'm looking at what comes through it. So it's a Gaussian bandpass filter. I don't remember the bandwidth. I think it's 20 or 30 nanometer semi-bandwidth. And its center wavelength varies linearly as we go up the y-axis. Visible wavelength range filter, and I'm illuminating here with CIE D65, which is a nominal daylight source. And we're going to assume when we view it that it's nominally daylight adapted. We assume that our eyes are adapted to the white of daylight when we're looking at this. So we're in a room that's maybe illuminated with daylight, but in a corner, we're glancing over and looking at the output of this filter. And so there are several things I can show you about this, and I'll show you that live in a minute. So let me just go to it, and I'm going to run it. It doesn't take too long to run. And this is tracing, if I remember right, it's probably on the order of 1 million rays. So it takes a few seconds, but it's not very long. What you're seeing here are the trace arrows of a subset of the rays because the plotting takes longer than the tracing. So I don't plot them all, but I'm going to use them all in the actual measurement results. For those of you who do a lot of analysis especially in non-sequential ray trace tools, that's a familiar concept to you, but if it's not, don't feel bad. Okay, so what we're seeing right now is not the tri-stimulus result we are looking for. Let's see, I'm going to, again, turn myself to visual appearance for each of these so that we see what they actually look like. And so we see a nice rainbow coming through, and we also see that in a display viewer type window here. This is nice if we want to do detailed measurements, basically know with precision and numeric precision what is going on at a particular place in the window. But for now, let's stick with the 3D viewer because in a sense that's what I build this talk about. So so we see, nice, it's a spectrum. And without further ado, I'm now going to go to the second flavor of the same problem. So now let's do this with an A source. Now the A source is sort of a prototype for tungsten sources, for sources that come from a heated tungsten filament. They are yellower than daylight. And so it's interesting. We call it a warmer color, but it's actually cooler in terms of black body. So the CIE tungsten source, which is yellower. And you see a couple of differences here, and I'll talk a little bit more about them live. So what I'll do is I'll start that running first, and then I'll come back and talk about the slides for a moment while we let the trace run. So back to the slide for just a moment. And so first thing we notice, yes, the source visual appearance is actually yellower, not approaching pure white. We can look at the correlated color temperature and draw some conclusions. And these are all interesting. So I might ask you, what do you notice about these two other than that the source is very white looking here and very yellow looking here? Let's go to the live view to talk about this a little more. So I'm going to turn on the visual appearance of the source, and I'm going to turn on the visual appearance of the result. And there are a couple of things that I find worth remark here, maybe more than a couple of things, but certainly at least a couple of things. So we look at visual appearance. It looks kind of a yellowish orange. And if you think about looking at tungsten sources, like when you look into a dark room, but you're daylight adapted, and there's this little glowing tungsten bulb in the corner, we can actually see that as being yellowish. And that's what this is telling us. And then if we look at the correlated color temperature, and while you see a lot of noise here, it's noise at a very small level. Basically, all these pixels are saying that the color temperature is somewhere between about 2500 Kelvin and 3000 Kelvin. And we're going to look at details in a couple of minutes about this that will make it even more clear. So just to go back to the PowerPoint and clean up, what I notice is that with a source that has a very strong yellow component, which is more heavily weighted to yellow than daylight, we actually see the yellow peak in the color that comes through much more distinctly than we do for the white source, the white daylight source. So this is a good result. And remember, we're always showing you what the daylight adapted eye would see. It's possible to do a chromatic adaptation to a different normal illuminant, to a different adapted illuminant, but we kind of thought that may be throwing a little bit more at you than you want right now. So interesting thing about this is, if you don't want to deal with how you do this in script, or you just plain don't quite see it yet, you can figure this out by doing it in the Optics Manager. So let me go back live. Remember, the last thing we ran was the CIE transmitted result. If I come over here to the Optics Manager and I open, and hopefully I haven't misplaced, the visual appearance of a bandpass filter analysis only. So there is no system definition, there is no source definition in this tree, but I can run the trace analysis by doing right-click trace analysis. I've got an illuminance measurement, a visual appearance, and a CIE graph, which is the three-pane result. And so if I say right-click, run analysis, then I'm going to get something very much like what I just showed you, but you're ready to do that without even knowing the command names yet. So to me, that's a fantastic result. So here you see this kind of yellowish transmission where the yellow peak is bigger, just as we did when we ran it from the script. And here we have the 3-pane window. And one of the really great things here, okay, we're looking at tri-stimulus X. If we want to change this to, for instance, tri-stimulus Y, we can. And we could also get a map of the correlated color temperature. So why don't I turn that on for a minute? Well, this is transmitted. So the correlated color temperature is actually not very instructive here. But the key is that we can look at all those quantities. If I really wanted to do something cool with the correlated color temperature, however, why don't I go back and don't be scared by the script. I'm just going to go down and I'm going to run just through source creation. We're not going to actually trace again. We're just going to run through source creation. And so I'm going to run to here, but I'm not going to actually do the chromaticity measurement. And it's all done. Now, let's go back to our Optics Manager thingy and run it again. So right-click on Trace Analysis, do a Run Analysis, and now let's look at the correlated color temperature. Okay, it looks kind of noisy, and man, that is hard to read, so let's get the magnifier back. So it runs from 2780 Kelvin to 28 something. Wow, that next digit's hard to read. I think 2820 or so. But just to be completely clear, let's look at the data. We don't have to rely on the graphics alone. We can scroll over and look at the correlated color temperature. So if we look at the correlated color temperature data, we see every one of these pixels here is enumerated with its actual correlated color temperature. Around 2800, give or take, most of these are within just a few degrees. So a very tight packed 2800 Kelvin source nominally. So I'm going to go back to the presentation, and I think we can clean all this up. So that shows you how to do this using Optics Manager. And you see, the key thing is make sure that your script gets at least to the point where you've set a CIE calculation profile. And it is as simple as CIE new, and then in single quotes, the name of the profile. Name it sensibly so you remember what you were measuring with this particular CIE analysis. And then it will keep the files filed by that name. So it really is a good idea to make sure that you do a CIE new for every measurement you want to do that is tailored to naming it right. There are other options, but you don't really have to know them yet regarding the resolution of the interpolation table and stuff like that. You don't have to know that to use this, and the defaults will get you a long way. So for now, I'll just tell you, don't worry about that. More detail, if you're interested, could be done in a later webinar. And this just shows what I just showed you for the A source itself, what the correlated color temperature looked like and how we did it. And these are the filter outputs done the same way, which I just showed you live. Please feel free to contact us. If you're interested in knowing a lot more about our products, feel free to talk to sales. In other words, if you might want to update, upgrade, or purchase, or get a trial, feel free to contact sales. If you actually have questions about how we do these things, then by all means, contact support@breault.com. For any questions, for guidance on modeling, for detailed usage and instruction, feel free to contact support@breault.com.
If anybody on the webinar is doing any projects that you'd like to share and you can get a release from your employer, we'd like to see them. We'd like to share them with our audience also. So if you have a project that you're working on that you'd like to share through Breault Research using NextGen ASAP, let us know. We'd like to share it with our audience. So that's the next thing. Again, if you have any questions that you think of after the webinar that are for sales, just go to sales@breault.com. If you have any technical questions, you're using the software, please send them to support@breault.com. Now, this message or this presentation is going to be sent out to all the attendees. You will get this in your email box in probably 48, 72 hours. So I want to thank everybody for attending, and everybody have a great rest of the day.